Okay, this is a video that will help on problems 11 and 13 from your equilibrium assignment. And you'll notice in the solutions to this assignment that are on D2L right now, that I use a method, an XY table method. I didn't use that method this year. I'll show you a different way to do it where you don't need the table, but it is the same result no matter what you do. So if you remember from the very first question on this assignment, it gave you sets of arrows and it asked you whether or not an object was in equilibrium. And if you recall, equilibrium means that the up forces, all the sum of all the up forces must balance or equal the sum of all the down forces. And also forces to the right equal forces to the left. I just say right equals left. Okay, and it was pretty obvious to you when it was not in equilibrium. So for example, this picture with 3 arrows is not in equilibrium because you would need a 4th arrow pointing left in order to put that into equilibrium. And so just using that idea, you can solve all these problems. So let's just do an example. If we had a force that was up at 60 newtons, on some object, and then we had a force that was down with 60 newtons and a force to the right of 40 newtons. And the question were, what is the other force that puts this into equilibrium? Well, just by looking at it, you could say, well, clearly we need a force left equal to 40 newtons. Okay, so if we can get our picture to look like this, where we just have up, down, left, right, it's pretty easy to figure out what we need to put things into equilibrium. So let's do another example. It doesn't have to be single forces. What if we had the 60 newtons up and the 40 newtons to the right, but we only had 20 newtons down? And the question is, what forces do you need to put that into equilibrium? Well, by looking at that, we need, you know that you need 40 newtons left to balance the 40 newtons to the right, but you're going to need some more force down because 20 newtons does not equal 60. And so you're going to need also 40 newtons down. Okay, so in that case, we needed 2 forces, one left and one down, to put the system into equilibrium. Now, whether this comes from 2 separate forces, one left and one down, or it actually comes from one force that is the hypotenuse of those two. In other words, the 40 and the 40 are components of a force. And remember what components are. They're the sides of the triangle, and the force itself is the hypotenuse. It could be either case. So it could either be there are actually 2 forces, the 40 left and the 40 down, or it could be there's only one force and it happens to be at an angle, and its 2 components are the 40 left and the 40 down. Okay, so if it says there's only one force and yet you get something left and something down, it means that the one force must be the hypotenuse of those 2 components. Now, just in case you forgot, let's just review this forces and being hypotenuse and stuff like that. So remember, when you have a force that is the hypotenuse, call that F, the components of that force are the sides of the triangle. And it doesn't matter whether you go left and down or you go down and left, it's the same triangle. And let's say we're going to call this one theta. But once again, it doesn't matter. You could call the other one theta and just reverse the equations. Now remember, this is the close side, this x component. So this is F cos theta. And then this is the opposite side. This is F sine theta. Okay, so there's 2 options. Let's just practice. If you know the force, so say the force is 20 newtons, and you know the angle is like 30 degrees. So if you have the force and you need the components, it's the same triangle. Then you actually work it out. This component would be 20 times the cosine of 30. And this side would be 20 times the sine of 30. Okay, so that's if you know the hypotenuse and you need the sides. But what if you know the sides and you need the hypotenuse? So we still know how to do that. because it's all the same trig. Remember the A, B, C. You've got Pythagoras. So say we don't know what the force is, but we do know the sides. So say this one is 40 newtons and this one is 30 newtons. And we don't know the angle. Well, we use the Pythagorean theorem to get the hypotenuse, 40 squared plus 30 squared. That's 30 newtons all squared. That would give us the hypotenuse. And then to get the angle, we use the inverse tangent, because remember, tangent is opposite over hypotenuse. So it would be opposite is 30, sorry, opposite over adjacent. Opposite over adjacent. Opposite is 30, opposite the angle, and adjacent is 40. Okay, so we got two things that you always have to do for these problems. The first thing is usually you're given the force and you find the components. And then in the end, if once you have the components, you go back and you find the force. And it may be a different force that you're dealing with. So let's do these problems and see how this works. So number 11, it deals with the kneecap, the patella. Okay, so it's got a very nice picture there showing the forces on that patella. And if I just draw the patella as a box and do the free body diagram, it says that the quadricep tendon pulls straight up with 60 newtons. And the patella tendon pulls along the tibia also with 60 newtons, but this is now at an angle. So we need an X, and it gives us 42 degrees. And the question is, what is the third force that puts that system into equilibrium? Now we can't decide what that third force is until we break this into left, right, up, down. So step one is to find the components of, all forces. Okay, so this is a case where we know the hypotenuse is 60 and we want the sides. So we need the X component and the Y component. So this would be 60 times the cosine, this is the close side, to 42 degrees. And this one would be 60 times the sine of 42 degrees. Oh, I don't know why that's doing that funny thing. Okay, and this happens to be 44.6 newtons. And this one happens to be 40.2 newtons. Okay, step two, you must redraw this. You no longer need that force at an angle. That's just going to confuse the picture. So step two, redraw showing only components. Only up, down, left, right components. Okay, we don't need that force at an angle anymore. We know it's doing two things. So we still have that quadricep tendon up here. But now the patella tendon is doing two things. It's pulling right with 44.6, and it's pulling down with 40.2. And now the question is, just like the one I talked about at the beginning of the video, what forces do you need to put that into equilibrium? Okay, so step three, find, that's supposed to be a 3, find components that put object into equilibrium. And you know it's in equilibrium because your kneecap doesn't fly off. So your kneecap is stationary with those forces pulling on it. There has to be another force or forces working on it so it doesn't go flying off down your shin bone. Okay, so you just simply look at it. Now this is where the XY table comes in. You could make a list and you could say up we have 60, down we have, and we put a negative 40. What else do you need to get to 0? And it would be a negative number. But I think it's better just to look at this and figure it out. So clearly you're going to need something left. Okay, so need 44.6 newtons left. and that'll balance that force to the right. But now we're going to need some extra down because there's not enough down. 60 newtons up does not balance the 40.2 newtons down. And so, and how much would we need going down? Well, it would be 60 minus 40.2, which equals 19.8. 19.8. And we know that's down because there's less down than up. Okay, so we need 44.6 left and 19.8 down. Okay, so let's just keep drawing this so we can see how it works. So we've got the 60 is balanced by two forces now. One is the, I should have made that longer, 40.2, and then the remainder comes from another force, 19.8. We've got the component of that patellar tendon pulling off to the right. So there has to be something left to balance that. Okay, that is now in equilibrium. So we know what all this is from. There's the quadricep tendon. This is the component of patellar tendon. I guess they call it patella tendon. This is also, so these are both components. Now the question is, what is this from? There's two forces. So do you think there's two different forces on the kneecap? Well, in fact, the deal is there's only one force, and these are the components of that force. And so because the femur bone pushes at an angle, it's got two components. And so it's got a left component and it has a down component, and that is actually from one force, which is the hypotenuse. And so it's the hypotenuse. This is the force of the femur on patella. Okay, so we know its components. Now we need the hypotenuse. Now, if it had said there are two more tendons or ligaments or something, and one pulls left and one pulls down, well, fine, that would be the answer. We've got the left and the down. But if it says there's only one force, which is the contact force from the femur, then those are the components, and we need to get the hypotenuse. Okay, well, we know how to do that. It's the hypotenuse is the force, and so it would be the square root of 19.8 squared plus 44.6 squared. And so that comes out to 48.8 newtons. And we can work out the angle that it acts at below horizontal. It would be the inverse tan of the y component, 19.8, divided by the x component, 44.6. And this would give an angle of 23.9 degrees, and we would say below horizontal. Okay, and that would be the answer to number 11. Okay, well, let's just carry on and do number 13. And it's exactly the same situation. We'll only do part A. Don't worry about part B. Part A is difficult enough for number 13. It's the guy hanging from two hands. Two arms. And we want to know what the force is along the arm. So the force on your arm is holding him up. Force of gravity is pulling him down. So we can get that force of gravity immediately. It's 75 kilograms times 9.8. And so that gives us 735 newtons. Okay, so exactly like the last question, step one is we need to draw this in components. So let's call this F arm 1 and F arm 2. Now these are along the hypotenuse. So once again, we're trying to find the hypotenuse. They don't tell us what the hypotenuse is. But so we're going to have to work with components. Okay. Now it does give us the angle, and it gives us a funny angle. It gives us this angle in here as being 20 degrees. Okay, you're probably used to having the angle next to the x-axis given, but that's okay. We know how to do our close with that 20 degrees. Okay, so just like step one, find components of the force. Now, you don't know the force, so you're going to ask, how do I find the components? Well, you're going to have to just do a bit of algebra here and draw it, and then we're going to see that the upward components from your arms have to balance this force of gravity. And there's two arms, so each arm has to take half the force of gravity straight up. Okay, so if I draw it again, your arms are doing two things. They're holding you up. That would be F arm 1 cosine theta and F arm 1 sine theta. They're also keeping you going side to side. Like if you let go of one hand, boom, you'd swing over to the right if you let go of your left hand. So that's arm 1, and arm 2 is doing the same thing. It's holding you up and it's pushing you the other direction. Arm 2 sine theta and F arm 2 cos theta. And then you got the force of gravity, the 735. Okay, now we can see that the force in each arm has to be the same because the angle is the same and they point left and right. So these two, this exactly to the right, exactly equals to the left. Those are in equilibrium. We don't have to worry about those. It's the up down that we have to worry about. We want to know, well, just how much of the vertical component, just this upward component, does each arm take? Well, it must take half of the 735, each of them. Okay, so we know, let me draw it again. So we know that one arm straight up has to be 735 over 2, which is, what is it, 367.5. I'll just keep an extra sig figure. And the other one as well has to be 367.5. Okay, and then we know down is 735. That puts it into equilibrium. Okay, now the question is, so I know the angle and I know one component, and now I'm trying to find the hypotenuse. So once again, we go back to our trig. So with that, let's just do one arm. So one arm only. I know that one arm has a component of 367.5 up. I don't care what it is to the right. And the hypotenuse, I don't know, but I need to find that. F arm equals unknown, but I know the angle, 20. And rats, I should have put that around here. That's this one. Okay, so this is a triangle where we know the hypotenuse. This is just like the trig questions that we did like way back when we did trig. So it's the A, B, C. Which ones do we know? This one we don't know. This we do know. And this we know, 367. So which trig function relates those? Well, you look at it, it's the cosine. So we know that the cosine of 20 degrees is adjacent divided by hypotenuse. And so that's how we're going to get this hypotenuse. We're going to multiply both sides by F, divide both sides by cos 20, and we'll get the force in the arm. Turns out to be 300. This is only one arm. Right, that's one arm. So then each arm must be 391 because everything's symmetric. This is just like the crutch question, where it's exactly the same as a crutch. It's an upside down crutch, right? So we've got the arm is like the crutch, and we know that the vertical components have to balance the weight. And so we did the same thing. We found that how much each crutch supported vertically, whether it's half the weight or a third the weight. If we're standing on one foot, it was a third the weight. And then once we know the vertical and we're trying to find the hypotenuse and we have the angle, It was exactly the same equation as we did for the crutch. Okay, well, I hope that helps. And email me if you have any questions.